This presentation we're going to talk about regular singular points, Frobenius' theorem, and the Bessel function. Let's take a look at a definition. An ordinary point. If we have a differential equation, a2 of x y double prime plus a1 of x y prime plus a sub 0 of x times y equals 0. A point x is equal to x naught is said to be an ordinary point if we can write our differential equation in standard form, and if we take our p of x and q of x functions after writing it in standard form, and we find that p and q are both analytic at that point x naught, then we have x naught as an ordinary point of the differential equation. If it's not an ordinary point, then it is said to be singular. And recall that analytic means there is a power series expansion around that point. A singular point can be further broken down into a regular singular point or an irregular singular point. If we take our function p, capital P, from the differential equation multiplied by x minus x naught, and then call little p of x that function, and also define q of x similarly, but this time with x minus x naught squared multiplied with a q of x function. If both little p and little q are analytic at x naught, then x naught is said to be a regular singular point. If these functions p and q are still not analytic, then we have an irregular singular point. We will be dealing with regular singular points. Frobenius' theorem allows us to find a power series solution around a regular singular point. So if we do have a regular singular point, we can have a regular power series solution that needs to be multiplied by some power of x minus x naught. And so your power series solution then would look like this, and it may not actually be a power series anymore, because this r, if this r is either less than 0 or is not an integer, which is possible, then this is officially not a power series anymore. But we can still consider it as a power series solution because it's based on a power series. Now, this r is yet to be determined when we do the problem. And so we're going to try to find a way to get r a little bit sooner through a formula and this equation called an INDICIAL equation. More often than not, we will be looking at power series or series around x is equal to 0. That simplifies things greatly for us, and so when we set up our Frobenius' theorem method of finding a power series, we're going to consider x to the n minus n plus r times cn. So finding r is a short process once we can identify p of x and q of x. Once we identify p and q, we'll multiply capital P by x and call that little p of x. And then, since this is supposed to be analytic, we can find a power series around x naught for this function. Similarly for q, we can find a power series around x naught for this function after multiplying it by x squared. What we're going to do with these power series is really just take the first term, so we don't even have to work hard at getting the rest of the series. We just care about the constant term. Once we identify the constant term, this formula r times r minus 1 plus a sub 0 r plus b sub 0 will become our initial equation after we set it equal to 0. Note that this indicial equation is a quadratic. So dealing with quadratic equations in the past, we know that there's three possibilities. We can have two distinct roots, we can have one real root that's the same, or we can have complex conjugates. Well, we were not going to consider complex conjugates, but we're going to further break up our cases into three cases. The first case is when the two roots are different and the difference is not an integer. It turns out that if it's not an integer, we're going to have a power series of a certain form. Our solution is going to be of a certain form. If the difference is an integer, it's also going to be a different form, and if the solutions are the same, multiplicity 2, it's going to be yet a third form. So what are the forms? When we have two distinct roots and the difference is not an integer, we simply find a power series for each of these roots and for each of these power series with n plus r1 and n plus r2 as a power. Case 2, if the difference between r1 and r2 is an integer, what we're going to do is we're going to find one power series solution first with an r1, the larger r1, and then with a smaller r2, the smaller root, our solution is going to be of this form where we could possibly have an ln function. Now this could possibly have an ln function. They threw in the c here because they say there's a constant that could possibly be 0, and if it's equal to 0, then we have only this part for y2, which is essentially the first case. But we want to allow for an ln because these functions that we would be finding, these coefficients might become linearly independent with y1. And it's possible that we might not even be able to find this. So this is a case where we could only possibly have just one solution that we can find. The third case is when the roots are the same, multiplicity 2. And so we're going to find our first solution the same way we found in all the other cases. And our second solution will have an ln function. The only other thing to watch out for is that your series that comes in your second solution does not have a constant term. And so the b sub 0 is 0. It doesn't have a constant term. We start with b sub 1. Here is our example, and here is a differential equation that we're going to work out. So our differential equation, x squared y double prime plus x y prime plus x squared times y is equal to 0. It's the homogeneous differential equation. Now if we divide out by the first, the coefficient function of the y double prime, we have in standard form y double prime plus 1 over x y prime plus 1 times y is equal to 0. So there we're able to identify our p and our q functions. Now that's capital P and capital Q, and for us to find our indicial equation, what we want to identify is our little p. Our little p is x times capital P of x, which is equal to 1, and our q is equal to x squared times q of x, which is equal to x squared. Now these are about the nicest functions that we can deal with. It's a constant function and a power function, so anything that's a polynomial is analytic around 0. So being that it's not analytic in capital P, but it becomes analytic in little p, it's analytic in Q and both Q's, but the fact that it's not analytic in big P but becomes analytic in little p means that we do have a regular singular point. So we're going to get to apply Frobenius' theorem. We need to find an indicial equation, so we identify little p and little q. Remember, little p is equal to 1. Well, we can find a power series expansion that's kind of not of any use except for the constant term, because we'll use the constant term in the indicial equation. We can also find q. A power series for x squared would look something like this, where it's zeros except for this 1 over here next to the x. Again, for the indicial equation, the only term that is important is the constant terms. So we got a sub 0 is equal to 1, that's the constant term for the p, and b sub 0 is equal to 0, that's the constant term for the q. So these two numbers we will use for our indicial equation. We put it in for a naught and b naught, and then we're going to get this indicial equation, which simplifies to r squared, and if we set that equal to 0, we're going to get r is equal to 0 of multiplicity 2. So we know that we're in the third case. We're going to first find our function, our first series, and then after we find our first series, we're going to attempt to find our second series using this form. So here's the beginning of finding our series. We're going to let y1 equal to this series. Oh yeah, remember that r is equal to 0, so really we're just looking at this series, and it looks just like our series for ordinary points. We need to put this into the differential equation, so we need y prime and y double prime. Remember, when we take the derivatives, and especially because r is equal to 0 here, the k is equal to 0 will not make any contributions. Likewise, k is equal to 1 will not make any contributions here, so we can afford to shift our indices. Let's put this into the differential equation. We have y double prime, x squared times y double prime, x times y prime, and x squared times y. Let's take this x and multiply it out. Our first series will have an x to the k power, index starting at 2. Our second series will have x to the k power starting when k is equal to 1. And then our last series will have x is equal to k plus 2, index starting at 0. So it looks like we have k, k, and then we're going to want to change this into k. So we do a shift on the index from k is equal to 0 to k is equal to 2. Everything else is the same. Now we take the first term here when k is equal to 1, and everything else here will be the three series put together when k starts at 2. And now simplifying this thing inside, this just becomes a k squared, and then we are ready to try to find or establish our recurrence relation. So now that we have our differential equation simplified, we can see that the C1 will become 0, and then we'll have the k squared ck plus ck minus 2 equal to 0. And that's going to give us a recurrence relation of ck is equal to negative ck minus 2 over k squared. Now, if k was an odd number, like 3, if k is equal to 3, this will refer back to C1, and C1 is equal to 0. If k was equal to 5, this would refer back to C3, which refers back to C1, which is equal to 0. And so all our CKs, where k is an odd number, will become 0, so they can all be taken out. Now we consider k, where k is an even number, and starting with k is equal to 2, it refers back to C sub 0. When k is equal to 4, it refers back to C2, which refers back to C sub 0. And then 6 would look like this, C8 would look like this, C10 would look like this. So we're trying to find some sort of pattern here. One pattern to notice is the alternating series, where it goes from positive, negative, positive, negative. The other pattern we note is that this is, we have 2 squared, we have 4 squared times 2 squared, 6 squared, 4 squared, 2 squared, etc. Now, that's not an easy pattern to write, but we found that there's a way to simplify this a little bit. We can take a look at 2 as 2 squared times 1 factorial squared. 4 squared times 2 squared is equal to 2 to the 4th times 2 factorial squared. And if we take 6 squared, 4 squared, 2 squared, if we take out a 2 from each of these, a 2 squared from each of these, so that's 2 squared, 2 to the 4th, 2 to the 6th, what we would have left is 1 square, or 3 squared times 2 squared times 1 squared. So 3, 2, 1 is a factorial, 3 factorial, and each of them are being squared, so this could be 3 factorial squared. Okay, and we can see the patterns as well. And if we take a look at the relationship now between the C and the C naught, the C sub even number, any even number, is going to be negative, plus or minus, depends on which n you're at, C sub 0, and this denominator is going to be 2 to that same index, and then half of the index factorial quantity squared. So this is our recurrence relationship for all integers, or this is going to be our function pattern for integers bigger than or equal to 1. So our first solution has that constant C sub 0, but if we leave that constant out and write it for the general term, we can just, for now, set it equal to 1. By setting that constant equal to 1, we have this series, and this series happens to be a special series. This special series is called Bessel's function of the first kind of order 0. It's of the first kind because it's the first solution that we got out of the 2 solutions that we're supposed to get, the 2 linearly independent solutions. So Bessel's function happens to be an important function in physics and engineering, and it is a solution to the differential equation that we're working on. And it turned out that this is just of the order 0, and we can have different orders, as you may guess. The graph of Bessel function oscillates, but the amplitude looks like it decreases. And there's a lot of other special types of properties for this Bessel function, the graph, and the function itself. So I would encourage you to look up the Bessel function and see what other kinds of information you can find. Now let's work on finding the second solution. If you remember the third case, our solution looks like this, where y sub 1 is the function that we found, the first function that we found, multiplied by the ln x, and then we have another series, but this time it starts with 1, and again our r is equal to 0 for this case. So we're going to need to identify this function and take its derivative so that we can put it back into the differential equation. So these two are being multiplied, so when we take the derivative we'll need the product rule, and here's a product rule for that, and here is the derivative of the series. We take the product rule again. This time there's two products to take care of, and then the derivative of that series. So now we put this y double prime, y prime, and y into the function. We put that into the function, and then we distribute the x squareds. So as the x squared gets distributed, we're going to get x squared for the first term. We're going to have x squared times 1 over x for the second term, x squared times 1 over x, and x squared times 1 over x squared, and so this doesn't have any more x's. X squared times the series changes our power from from k minus 2 to k. Similarly, we do this distribution for this x into the y double prime or y prime. We get an x there. We get a 1 over x, so that gets rid of that. And into the power, we get x to the k. Finally, this x squared being distributed to the last term. The last term only has two terms. The first term in the series, the x term goes up by k plus 2. So what we're going to do is we're going to collect all the terms that have an ln in it and combine those two, or those three terms together. And we realize that when we take a closer look at this is, if you look at j sub 0 as our function that is supposed to be a solution to the differential equation, it looks like it is in fact the differential equation. We got x squared times y double prime plus x times y prime plus x squared times y, and according to the differential equation this is equal to 0. We should also, the ln term, this whole thing goes to 0, and we can collect some couple of terms here. We got 2x j prime. We have negative j sub 0, positive j sub 0, so that's gone. And then we have 1, 2, 3 sums that we'll try to put together in a minute. So there is an index shift over here so that we can get the powers to be the same for x to the k, and then we can also, just like before, take that index of k is equal to 1 and move that out here. So we have the outside term, the k is equal to 1 term, and all the rest of these gets written into one series. And the series kind of looks familiar. It looks just like the first solution that we had. But unfortunately, this j sub 0 prime will have another sum, and so in terms of setting it equal to 0, we need to make sure we match the coefficients of the x's, and we need to expand our j sub 0 prime. So here is the derivative of the first Bessel function. So this used to be x to the 2n. That becomes x to the 2n, that power, and then we subtract 1 from the power. Everything else is constant, so that's the only change. And we put that into the 2x times j sub 0 prime plus all the other stuff. And integrating this, not integrating, but putting this x into this x will give us x to the 2n, and then there's an extra 2 over here that we can look at as 4. And so we want to combine these things to see if we can come up with a pattern. Combining this might be a little difficult, so what we can do is we can break this up into finding the first few terms of each of these series to see if we can find something. So if we say n is equal to 1, we're going to get this first term, or the x squared term. N is equal to 2, we're going to get x to the 4th term. And then there's going to be an x to the 6th term that we'll take a look at later on. The b1 times x is still here. Now if we expand this, when k is equal to 2, and k is equal to 3, k is equal to 4, etc. Now a few observations here. This series has no odd powers, and every other x that we see here is x squared, x to the 4th. We have an x to the 3rd over here, but this is the only x, so this is the lowest degree that we have. And if we're going to set this equal to 0, then b sub 1 is going to equal to 0. Now, all these other terms, these are all even terms from the Bessel function of the first kind. And then we have these recurrence relations that we can find for the odd terms. And so, because there are no odd terms in the Bessel's function, and these odd terms are all together, separate from the even terms, and b1 is equal to 0, we can conclude that all the b's with an odd index will be 0. And the other piece of information to note is that we have a b naught here, but if you remember back, the form that we had starts with n is equal to 1, so there is no b naught. So b naught in this case would equal to 0. What does that mean? That means this is 0, and all these are 0, so that's going to be gone. And what we could do is we can just match, and the b naught is equal to 0, so those are all equal to 0. Now let's simplify some of these. The first term here, and then this term over here has an x, and the b naught is being 0 tells us that this all we have left is 4b2 times x squared. So those are your x squared terms. So after that you add x to the 4th, x to the 6th, etc. So if we keep this out, we can put the x squared coefficients together into -1 plus 4b2. Everything else now will follow our pattern. Now this didn't follow our pattern because the b naught disappeared, so we wanted to take that out. But everything else will remain the same, and we can follow that pattern. So in following that pattern, we're allowed to combine these two series, these two sums, into one so that we can find our recurrence relation. So here's our leftover, and we want this to equal to 0, so that's going to imply that b sub 2 is equal to 1/4. Meanwhile, we have this big mess over here that is going to help define a recurrence relation for our b sub even numbers. And it looks like b sub 2n is going to equal to b sub 2n minus 2 negative over 2 squared over n squared minus, and then we have an alternating negative 1 to the n, and then we have the 2n, 2 raised to the 2n times n factorial n squared, and then we have this extra n that came about. So let's try out some few values for n here, like when n is equal to 2, because this starts at 2. So we get b sub 4 is equal to b sub 2 negative 2 squared over 2 squared times 2 squared minus, now this is a negative 1 to the second power, so that's positive 1. This is 2 to the fourth power 2 squared squared, or 2 factorial squared times the 2. And remembering that b2 was equal to 4, or 1/4, we can put that 1/4 here. And then if we notice between these two, negative 1, negative 1, the 2 squared times 4 is the same thing as 2 to the fourth power, and then 2 squared is the same as the 2 factorial squared. So everything here and here are all the same except for this extra 2. So if we factor out this negative 1 divided by 2 to the fourth times 2 factorial squared, we're going to have a 1 left here minus a 1/2 left here, and so that's what you have factored out. Might seem strange, but that's how the pattern is going to come up. When n is equal to 3, we have b sub 6 is equal to negative b sub 4 over 2 squared times 3 squared minus, this is negative 1 to the third power, so it should be negative, 2 to the sixth power times 3 factorial squared times 3. Now what's b sub 4? B sub 4 is equal to this whole thing. This is b sub 4. So we have negative 1, 2 squared times 3 squared times b sub 4 minus this thing that didn't change, except I forgot my negative sign. Well, it turns out that this term becomes a positive 1. The 2 squared and 2 to the fourth become 2 to the sixth. The 3 squared times 2 factorial can get merged into a 3 factorial squared, and so that exactly is what we have here, and if we take that out, we have a 1 plus 1/2 plus 1/3. See if we could do this one more time. N is equal to 4, so we have b sub 8. That's equal to negative b sub 6, 2 squared, 4 squared, because n is equal to 4. Minus, we have negative 1 to the fourth power, which is positive 1, 2 to the eighth power, 4 factorial squared times 4. What's b6? b6 is equal to this. That was the previous sum that we got. And if we combine these terms, we should get it to match with this. So negative plus a positive, negative times a positive is a negative. So this is a negative that we're going to factor out. You got 2 squared, 2 to the 6th, that's 2 to the 8th, so we get to factor that out. We got 4 squared and then 3 factorial squared. Now put that under square, you got 4 times 3 factorial, which is 4 factorial squared. So that's everything here, and that's almost everything here except for this 1/4. So if we factor out that negative 1 over 2 to the 8th and 4 factorial squared, we have 1 plus 1/2 plus 1/3 plus 1/4. So that's our pattern. Now if we denote this sum, 1 plus 1/2 plus 1/3 plus all the way to 1 over n as Sn, then we can replace that sum that we have with just Sn. And so now that we have a pattern for our b's, we can put it back into the second equation, or second function, where you have y1 times ln x plus the sum with the b's in it, and this is the b sub k. It turns out that this solution can be rewritten a little bit so that it would still satisfy the differential equation as a gamma, a constant gamma, minus the ln of x over 2. So more commonly it would look like this. This is our well, what's gamma? Gamma is this weird constant. It's known as Euler's constant. And so this is Bessel function of the second kind of order 0. This is a second function solution to our differential equation. So this is another special type of function. It has a graph, and this is a graph associated with it. And again, this is of order 0 that depends on the Bessel function of order 1, or of the first kind. And so there are other Bessel functions, again, the j sub 0 and the y sub 0 is the second kind, the j sub 0 is the first kind, the y sub 0 is the second kind. And there's other types, other orders that you should consider examining and looking at too. It's very similar to our differential equation. Okay. So I hope this gives you some insight to some interesting solutions to differential equations, the power series solutions, and these are pretty popular functions when you get into more physics and engineering courses.